Okay, the last lecture was about interfaces, so today we will continue this topic. I finished talking about this slide, so at the beginning of the lecture I showed you what is the problem when we send data and there is a difference between the receiver and transmitter base time. So even the difference is not so huge, after some time we can observe errors. So I mean we can find additional bits or lack of particular bits in data stream, depending whether the duration of single bit for transmitter or receiver is longer or shorter. The solution I showed you was self-synchronization. So the receiver can synchronize or can detect beginning of new bit by using edge. So if there is a level change in signal, it may reset its counter, and it can observe or count duration of particular bit starting from this point, so from edge. This mode I mentioned before is called an asynchronous mode. So it means that data between transmitter and receiver is sent asynchronously. So without any pace, yeah. So the other possibility is asynchronous mode. So I'd like to show you this solution. It is used for now, okay, but let's say 10 years ago, it was used more often, but now it's not so popular. So what is the synchronous mode? We have two lines. So when we want to send data, we have to connect transmitter and receiver using two lines. So on the first line, which is called data line, standard data stream is presented. Yeah? So we have level changes depending whether there is 0 or 1 bit. We can apply different methods of coding. Okay, but the second line is clock line, and the clock line changes its state on every bit. So, for example, here we have bit 1, it is low. Next bit, it is high, and so on. So it tells receiver when data are ready to read. Usually, to better synchronize, the ready or data bit readiness is indicated using edge, not level. So when the state is low, data are changed, or a state of transmitter or data line may change, and when the clock change its state, it triggers read of data line on the receiver side. So in this case, you can see that there is no problem with synchronization because every bit is indicated. Yeah? In this case, you can see that the read command is on the rising edge, but there are some solutions for which operates on two edges, or they operates on levels. Yeah, it depends on implementation. So it seems that it is very efficient solution which led us to avoid synchronization problems. And it seems that it should work for even very high-speed interfaces. But in fact, you can see that synchronous transmission is used for PCI, which seems to be quite old interface in computers. For memory bus, okay, which is the fastest interface in our computers. For E2C or SPI, which are interfaces used for microcontrollers, not for computers. So you can see that there are no interfaces like HDMI, USB, PCI Express. So they are not synchronous interfaces. So what is the problem with clock line? Okay, I will answer this question later. Okay, if we consider asynchronous interfaces, the difference between synchronous is that there are no clock line. We have only a data line, so we have to ensure, let's say, self-synchronization of a receiver. Therefore, different solutions are used, so mostly channel coding. So let's say the most popular now is XB over YB. So for example, 5B over 6B or more. Or using special frames. So if we use frames, we try to pack bits into frame, and if we're using frame, we ensure that at least the level change at least one time per frame. So frame has special additional bits which generates a level change. And in this case, the receiver can detect the begin and the end of the frame. So even additional bit was added for some bit, it is able to detect it. So this error is not propagating over for the next data which will be sent. You can see that even this interface seems to be more sophisticated, so harder to, okay, in physical meaning, it's easier to implement because we have only a single wire, yeah? But in looking at the problem of self-synchronization, it seems to be more difficult to implement. But you can see that the most current interfaces use this asynchronous mode. So we have USB, serial ATA, PCI Express. Okay, we have also a wireless interfaces, yeah, Wi-Fi, Bluetooth, Firewire, Ethernet. They are wire interfaces, but they are also asynchronous. Okay, so what is the problem with synchronous interface? It's not so popular now. The problem is quite, interesting. Do you know what is the average speed of baud rate for the fast interfaces like Serial ATA or PCI Express. So let's say what is the frequency or bit frequency? So how often the bits are sent? Yeah, gigabits per second, of course. So let's say we have gigahertz, yeah, frequency. So look, gigahertz, it means that duration of every bit is 10 to power minus 9 or even less. So in this period of time, we can try to calculate it. So let's say that we want to calculate what is the distance which light can pass in time of a single bit duration. So let's say that we have interface of 1 gigabit per second. It's not so so huge frequency. So we have 10 to power minus 9. And we want to multiply it by speed of light in vacuum. Yeah, so we have 300,000. It is kilometers per second. Yeah, I think so. So to calculate it in meters, I have to add additional 3 zeros. So now I have the distance which light pass in time of a single bit duration. So you can see that it's 30 centimeters in vacuum. But if we assume that we send data by wire, the electromagnetic wave flows slower than light in vacuum. So what is the problem here? The problem is that if we have two lines and they differ in, in length or in physical properties like conductance, or they have different capacitance, the time, if we send particular impulse synchronously, at the receiver side, we can observe lag. So if two lines are not perfectly, matched, you can observe that, for example, in one line, the impulse will arrive faster than for other line. So it is physics. So on the frequency like gigahertz, you can observe these effects quite often. So in this case, it's hard to achieve synchronization because it may happen that the trigger pulse of clock line will arrive, earlier or later. So it will arrive when data line is changing or it's not valid. So therefore, the external interfaces are mostly asynchronous. The only interface which is synchronous in our computers is memory bus, which is, printed circuit board. I will show you some pictures of memory bus interface, but it is printed and it is perfectly fitted or suited. So there are no difference in path lengths. Sometimes when you look at the main board or some high frequency printed circuit boards, you can see that some paths there are some meanders on paths because we have to align the path length. So this element has to be considered when you have so high frequencies. It is impossible, or let's say, So it is almost impossible to achieve so high precision for external interfaces. So if you have your USB cable and you should, or manufacturer should ensure that every path is perfectly aligned and has the same physical properties. Okay, in theory it is possible, but such wire, if cable will cost much more than ordinary user is ready to pay for it. Yeah, of course. So therefore we have synchronous interfaces, asynchronous interfaces. Okay, so now we have to classify interfaces, not only looking at whether they are synchronous or asynchronous, but we can classify them using different approach. So using serial, parallel, or parallel set of serial interfaces. I will answer or explain what does it mean. So this is the method of transfer and mode of transfer. So we have simplex, half duplex, and full duplex interfaces. Simplex, it means that it is one direction interface. So like during lecture, yeah, okay, let's say in lecture we have half duplex, but in simplex, it means that only we have the transmitter can send data to receiver, but it is not possible to send data in opposite direction. In half duplex, at the same time, only a single node can send data. And in full duplex, it means that we have two nodes and they can send data to each other simultaneously. So there are no restrictions. So full duplex is similar like your mobile phones, when you can hear and talk at the same time. In half duplex, like lecture, yeah, when I talk to you, you try to listen, and then you can ask some questions. And in this case, I try to listen you. So okay, but we start from the method of data transfer. So look, in parallel interface, we have several data lines. So far I showed you only examples, which was the, let's say, serial interfaces. So we had a single data line, we send data, and on the opposite side, the receiver reads bit by bit. In case of parallel interface, we have several data lines. So we can tell that data or bits are transmitted simultaneously. So assuming that we have 8 data lines, so every byte is splitted over, so 8 bits are splitted over data lines and they are sent at once. So similar transfer was observed here. Yeah? So we have different or 4 channels, and we send this data simultaneously. So we take 4 bits. No, we take 8 bits and we encode it over by using 4 data lines. So this is the example of parallel interface. In simple application, we can imagine that we have 8 wires and every bit is sent using separate layers. So in a single clock cycle, we can send 1 byte if we have 8 data lines. So what are the examples of parallel interfaces? In computers, we have memory bus. And here you have examples of older interfaces like parallel ATA. So it now it isn't used. Now we use serial ATA. We have PCI. So sometimes in some computers we can still find it, but it is mostly replaced by PCI Express, which is not parallel interface. AGPU, which was used for graphic cards, now it is not used. We use PCI Express. Very popular interface for connecting scanners and printers was LPT. Now we use USB. Yeah? So USB is also universal serial bus. So it is not parallel but serial interface. Ethernet in this format, which I showed you before. Okay. So you can see that mostly the older interfaces are parallel interface. Okay, about HDMI, I will tell you something. It is not true parallel interface. So what are the problems or maybe advantages? If we have parallel interface, in theory, we can send data ND times faster. Mr. Korzeniowski, ATA, yeah, parallel ATA and IDE, yeah, these are the same names of a single interface, yeah. Okay, so the benefit is that if we multiply number of lines, so we have not 1 data line, but we have, let's say, 8 data lines. In theory, if we use the same bit duration or data frequency, we can achieve ND times improvement. Yeah, so we can send ND times more data. Yeah? So, okay, but this is theory. What are the problems with parallel interfaces and why they are not so widespread? So the most problematic thing is bit race. So I showed you, I told you about bit race, talking about clocks. So the same problem, which was with synchronous interfaces. So there is a lag between the time when particular bit arrives, and it depends, or it is due to different physical properties of the medium. So the same problems may occurs here. So if you have 8 lines and they are not perfectly aligned, there are some physical differences between them, you can observe that some bits will arrive earlier or later than the clock line. Yeah? So in this case, we are not able to read the valid data. So how we can solve this problem? We can limit the interface frequency. Yeah. So look, in theory, if we have a serial interface to achieve the same throughput, like the same as for parallel interface, for serial interface, the frequency has to be n times higher. So let's say, in theory, if we want to have interface of speed, let's say 1 gigabit per second, it's enough to have parallel interface with 8 data lines, which speed is 8 times lower, so 128 megabits per second. But even though it is easier to build a serial interface of higher frequency than parallel interface of the same frequency, of 8 times lower frequency. So so you can see that for parallel interfaces, external parallel interfaces, we are able to send data, let's say, up to 2 megabits per second. If we want to increase this frequency, external interfaces can't do it. If we use a printed circuit boards and we are able to adjust the path length, we are able to achieve higher frequencies. But this process has to be very accurate. The second problem when we talk about parallel interface is crosstalk between lines. So if we have high frequency, the duration or the edge or the change of the level is very rapid, and it may induce some current and potential in neighboring line. So it may happen that if neighboring line is 0, but all surrounding lines changes from 0 to 1 or from 1 to 0, on this line we can observe disturbance. So potentially the receiver may detect additional bit or improper line state. Okay, so now I'd like to tell you something about transfer interfaces, transfer architecture, so about mode of transfer, so this classification. So the most commonly used architecture for computers is something which is called point-to-point. So point-to-point means that we have only two nodes, two hosts, and data is exchanged between them. There's another possibility. So we have a bus architecture where we have more nodes. In general, this architecture is used, for example, for serial ATA architecture. But look, even we have point-to-point connection, we have several possibilities. So we can have simplex or half duplex transfer. So in half duplex, I told you that at the same time only a single node can transmit data. While for full duplex, both nodes can send data at the same time. What are the benefits of point-to-point architecture? So in this case, okay, if we have half duplex mode, usually we have some, usually one side is more important than the other side. So one side is called master and the other side is called slave. So the master side is able to send data anytime, but the slave side can send data only when a host allows for it. In case of full duplex, these nodes can be equally important, so every of them can send data at the same time. The most common example of full duplex interface using point-to-point architecture is serial ATA. So in this case, the hard drive and the controller can send data at the same time. The second solution, which is not point-to-point, is called a bus architecture. So in bus architecture, we have many nodes, and they share the same transmission line. So what are the problems here? The most important problems is who can or who is allowed to transfer data, because if particular node transfer data, other nodes has to listen. So if more nodes start transfer data at the same time, there are interference of data, so we can't recover it. So there are several methods which led to avoid something which is called collisions. So the situation when two nodes start to transfer data. So what's the possible solution? The most commonly used in computer networks like Ethernet is something which is called a competitive access and collision detection. It is denoted as CSMA-CD. And I will tell you something about this method later, talking about network interfaces. The second method, which is used in industrial networks, is something which is called competitive access and collision detection and collision avoidance. Yeah, so we have not CD like here, but we have CA. And here you have a scheme which shows how this method works. So before the node starts to send data, it transfers something which is called a pilot sequence. So here you have 3 nodes, 1, 2, 3, and here you have state of bus. This method is used, for example, in CAN bus. So CAN bus is very commonly used in automotive. So in current vehicles, most systems are connected using CAN. So there are no separate wires which connects your lights with the controller or board computer or your air conditioning system or other devices or peripherals in your vehicle. But they are connected using 2 wires, and these wires are shared among all the nodes. This interface is called CAN. What is the typical for CAN and other interfaces like this? This is typical that we have 2 states, so we have high and low state. So we are able to encode 0 and 1, but only high state or low state is dominant. So if we have 2 or more nodes and one of them will send high state, this state is dominant. So on the bus, you will observe a high state. But if others node would send low state, and so you can see the node 1 sends low state, but node 2 and node 3 sends high state. So in this case, on bus, we will observe the high state, not low state or something in the middle. Yeah. Okay, so what happened? When particular node transfer data, it reads also the state on the bus. So it verifies whether the state on the bus is the same like the state it is intended to be. Yeah? So if it sends a 0, but it observes 1, it means that there is another node which transfers data at the same time. So in case of collision avoidance protocol, it stops transfer data silently. So it detects collision, but it stops transfer data. So now we have node 2 and node 3 which sends data. So far, these values are the same. Okay, here we have as long as these values are the same, nothing can be detected. But if something is changed, you can see that, okay, the particular node is able to detect it. So here you can see that there is a problem. So this image is not consistent with because okay, here the node 3 sent high state while node 2 sent low state, and you can see that nothing is changed. I told you that in Canvas the dominant state is high state, so we should observe. Okay, so something was happened with my internet connection, as usual at the university. Okay, so look, something is inconsistent with this example. I think that for CAN bus, the high state is dominant. So in this example, the node 3 should win this competition. Yeah, so node 3 should send data farther, while here node 2 will do it. But I think the most important is you to understand the idea how it works, because you know whether the high state or low state is dominant. Okay, in fact, it doesn't matter. It depends on the implementation of the interface. But the benefit is that at the one node is able to transfer data without any obstacles. So depending if we have pilot sequence, we can generate this sequence for every node on this way that the most important nodes will always win the competition. So if we have critical circuits here and 3 or more nodes will start some data at the same time, the most important nodes will win the competition. What are the, so here we have a lot of benefits in comparison to collision detection. I will tell you about during the next lecture. In this case, the collision are solved on different ways. So if the collision is detected, every node stop transferring data. So after random time, they start to do it again. But in this case, there are no problem with, you know, okay. In this case, at one node is able to send data. So there is deterministic time in which the most important node will be able to transfer data. So this is the real benefit. In collision detection method, we can imagine that the collisions, even we detect collision and the nodes will retransmit data after the random period of time. It may happen that the collision may occur quite often. So this method doesn't ensure a deterministic transfer time. But what are the problem with collision avoidance? We have to add a pilot sequence, so it takes time. So this is additional payload we have to add to our message. So in fact, if we are interested in sending a huge amount of data, adding additional information or extra data to every package okay, we lost an interface throughput. Okay, so these two methods belongs to architecture in which every node is equal important. Okay, we can add some additional we can modify a pilot sequence, but in fact, they are equally important. The second solution or approach is using arbitration. So in this case, there is a supervisor device which allow or which generates some permission for every node to send data. So there are two solutions. So we have centralized interface. So we have a master which governs the bus and lets particular node to send data, and we have distributed. Yeah, so like in CAN. So there is a method in interface which lets to determine who is allowed to send data. Okay, I think it's not so important. So now I'd like to tell you something about the master-slave architecture. So still we have bus and we have also some way of arbitration, but it is implemented on different way. So in this scheme, we have many nodes which are denoted as slaves. So they are dependent and they are not allowed to send data without permission. And we have a single node which is called a master, and only master is able to transfer data anytime. Yeah? So if the master allows or give permission for a particular slave, this slave is able to transfer data to master. So in this situation, we usually has transfer mode, which is denoted as half duplex. So at the same time, only one side is able to publish data. And the topology is similar to tree-like topology or star topology. It depends on what you see. So there are several solutions. Here you can see the scheme for Bluetooth interface, but this topology is applied for different interfaces. So it's not only limited to wireless interface. There are two possibilities how master is able to verify whether particular slave needs to transfer data. So these methods are used using polling or using interrupts. So first, what does it mean polling? In case of polling, the master has to ask or request every slave in some periods or intervals of time. So it has to answer, let's say, slave 3, whether it has any information to send, and then slave 3 is allowed to send data to master. So this process needs to be repeated quite often. So you can imagine that we have several devices like in computers. So we have a keyboard, mouse, pen drive, and other devices. They are connected using USB. USB is bus architecture, so the same. We have shared channel, and we have many devices connected to it, and we have bus controller. And in USB, the controller has to poll every device and ask device whether there are some important information. So try to imagine that we have mouse. So if we want to achieve the high mouse responsiveness, the controller has to query mouse quite often. But if we have many devices, it takes a lot of time to do it. Here you have an example. So master sends a request package to every device. So here master sends to slave 1, and slave 1 answer. It sends to slave 2, and slave 2 answer again to slave 1, to slave 2, to slave 3, and so on. The polling policy may be, different for different devices. But if the master doesn't request particular slave, it has to wait, even there are very important information. So let's say for mouse, it's okay. But if we have, for example, a security button, so button which protects us against some accidents, and we connect this button to bus, and it will be handled in polling mode, it may be very difficult to ensure the higher responsiveness. If something hang in master, or maybe if this transfer will be longer than we expected, and we ask or poll this button, okay, several milliseconds or 100 milliseconds later than we assumed it should be, we have the accident may happen. Okay, so remember that it's not perfect solution. It occupies a lot of master time to verify whether the state of particular slave. So for many slaves, it seems to be inefficient, but in fact, this method is used in many interfaces like Bluetooth, like USB. The second possibility when we have master-slave architecture is using interrupts. So still, we have bus, which is shared. So slaves are not allowed to send or transmit data without master permission. But slave or group of slaves are connected to master by using additional, let's say, connection or additional interface. And this interface or this connection is used only to indicate that slave has something to send. So in this mode, master doesn't poll slaves, but if slave has any data to send, it generates something which is called interrupt. So it may send a high state on interrupt line, and then master verifies who called this interrupt and give the permission for particular slave. Or if the interrupt channel is shared among several slaves, it polls the slaves, but only the slaves what happened. Okay. So looking at the master performance, the interrupt seems to be even better because the master doesn't need to poll every slave in some intervals, but it can only react when something real has happened. So in general, interrupts decrease time of the inefficient master activity. Yeah, we can assign some priorities for interrupts, so master knows who should be handled first. The second or the third benefit is that every device can use several interrupts, so it may communicate to master several things. Yeah. But what is the benefits of polling? So it's simpler than interrupts. Yeah, you can imagine that. Okay, we have master generates its own program, and asynchronously interrupt is called. So it has to stop its work and have to switch to interrupt service routine. Yeah, so it make the program much more complex. The second benefit of polling is that we don't need additional lines, because in case of interrupt, we have to physically connect master with additional wires. So for example, for wireless interfaces, it is impossible to do it. So we can only do it for peripherals which are embedded on mainboard or physically integrated with your computer. So for external peripherals like pen drive, like displays and any other devices which are connected using USB, HDMI or other interface, it's impossible to give interrupts. So they are handled using polling. So in case of polling, in theory, we can connect any number of nodes. In case of interrupts, we can connect as many nodes as we have as the number of interrupts, or we can, combine polling with interrupts. So We have limited number of interrupt lines, but they can be shared among several nodes. So about disadvantages, you can see that disadvantages is for interrupts are some features of polling. So the first disadvantage is that for interrupts we need additional lines. Okay, in PCI Express there are some interrupts which are solved on different way, but let's assume that interrupt means that we need additional line. And the second disadvantage is that the architecture of master is much more complex. And during programming, I think that some of you has programmed some microcontrollers like STM or AVR, maybe not in Arduino mode, but if you do it, from scratch, you know probably something about interrupts, which are very useful, but they makes our program much more complex. Disadvantages of polling, I mentioned about them. So polling is much more, so it makes the master more busy, yeah? So it's time consuming if we have many nodes and they are usually inactive. Okay. What about applications? So I mentioned about the applications of polling and interrupts. So interrupts are usually used in integrated systems. So we have peripheral, which are physically integrated with the controller or master side. In case of polling, the polling is used to peripherals which are not constantly connected to device. So we have external devices, we have wireless connected devices, and so on. I don't spend a lot of time to tell you about this issue, but it seems to be very interesting to know. Okay, this issue is out of scope of this lecture. Yeah, I intended to make you some perspective or to show you some timeline of internet. So look, the first transatlantic telegraph cable, it was a very interesting story which started on 1858. Yeah, so the first cable was connected the Europe and the United States. So what was the story is very interesting from several perspectives. First, the guy who did it and who created or founded a company which built the first transatlantic cable. He tried to do it, I think, 3 or 4 times. So he spent a lot of money for the first 2 or 3 attempts, and it turned that you know, at the end, the cable was broken and everything was lost. After the third attempt, I guess it worked, I think, 1 week, and then it was broken and so on. But he tried again and again, and finally it was able to create a cable which were much more robust. But the first message which was sent, it takes 2 minutes to send a single character, yeah, so a single word. So the rate of was 0.1 word per minute. Yeah. So from current perspective, when we are able to stream, let's say, megabytes per second, it seems very low, but you should know that in these times, the sending message from Europe to United States was using ships. So it takes 1 or 2 weeks, or maybe not 1, 2 or 3 weeks to send a message from Europe to US. So it was in fact a breakthrough technology. And in 20th century, the system was able to send 120 words per minute. So you can see what was the progress from this time to now. Yeah. Okay. Now I'd like to start talking about particular interfaces in our computers. So I start from a rather old school example. So here you can see the architecture which is not longer used in computers, but I think that it's good scheme to understand how interfaces work and how they evaluate from in the range of, let's say, 10 or 15 years. So I think it's a good entry point. So look, we can think that the most important element in our computer is processor. So something which is called CPU, Central Processing Unit. In this time, so let's say 10 or 15 years ago, the CPU was connected with other peripherals using bus, which is called FSB, Field System Bus. So this bus was shared among other devices. But let's try to look at the FSB. So it led to connect processor with memory and other input-output devices. So this interface was parallel interface. It was consisted of, I don't know whether it is written here, but as far as I remember, it was consisted of more than 100 lines. So it was parallel interface where we have many parallel lines. Some of them were used to send data, some of them were used to send address and control. There was a clock So the throughput of this interface was up to 12 gigabytes per second. So regarding current interfaces, it is rather good throughput. But regarding the interface which connect processor with every device or every peripheral device, it was a bottleneck. So it decreased the performance of the processor. Now there are no FSB. There are some other interfaces which are denoted like QPI for servers or MSB for other devices, other architectures. And the throughput is even higher, but I will tell you something about this later on. So look, we have processor with the interface of speed, let's say 10 gigabits per second. And it is connected to something which is called a North bridge. So the North bridge was the controller or bus controller which governed the bus. So it was, let's say, kind of master or supervisor of the bus. So it allowed to transfer data to memory, to graphic card, and to other devices. So you can see that the memory was connected to North bridge, and to North bridge there was connected high-speed devices like display or graphic cards or other high-speed devices. The North bridge was also connected to something which is called South bridge. So the South bridge governed the the interfaces of lower speed or devices of lower speed. So when data were or when processor requests some data from memory or from hard drive, the South and North bridge governed this process. So they tried to optimize the bus usage because, as I told you, talking about data storage, the throughput of hard drive or even solid state drive is significantly smaller than throughput of the memory. Yeah? So therefore, when the particular information is requested and it has to be taken from the hard drive, the system has to balance the transfer. And remember that if we request data from hard drive and they are sent on, relative low speed, but they are sent using FSB. So at the same time, nothing can be read from memory or nothing can be sent to graphic cards and so on. So therefore, even we have relatively high throughput for this interface, this throughput is decreased by speed of peripherals or slower peripherals. Okay, so what happened in this period of time, let's say in the period of 10 or 15 years? So here you have a server architecture. So we have multi-processor system, but we can discarding processors here, and when we leave a single processor, it will be still true for personal computers. So look, in this entry time, the processor was connected to, oh, by the way, the north and south bridge are integrated in something which is called a chipset. So even most of user thinks that the CPU is the most important thing, the chipset is equally important. So if you buy a main board with bad chipset, and you buy a very good processor, okay, you lost a lot of money for it, because the chipset determine the real speed and performance of the processor and other peripherals. Okay, but look, we have chipset, and chipset is communicated with memory and communicated with other devices, and with south, so the north bridge will communicate with south bridge and so on. Okay, so for front side bus, we had 140 lines. The clock was 40 megahertz. Okay, in some cases it was overclocked to 700 megahertz. And the speed was like this. The front side bus was half duplex. So at the same time, the processor could read data from peripheral or send data to peripheral, but only to single peripheral at the same time. Yeah. So, okay. So now look what happened in time. If we have several CPUs which were connected to FSB, after some time, they were communicate with North Bridge using dedicated interface. So they doesn't share the same bus to communicate with North Bridge, but still memory was shared among them. So the memory was handled by North Bridge. But the next step, which was very, I think, important step, which was which enabled to improve the processor performance, was to embed, so the memory controller was integrated with processor. So still we have North Bridge and South Bridge, but the memory controller is embedded into processor. So now the processor is able to read and write data to memory, and at the same time it is able to communicate with other devices. Probably you know that current processors, they have also the PCI Express controllers. So now they are able to communicate not only with memory, but they are able to communicate with PCI Express devices too. So communicated to chipset is used to operate with devices of lower speed, like hard drives, sound cards, and etc. But what has changed here? So FSB was replaced by point-to-point interfaces. So they are not buses, so they are not short, but they connect processor with, let's say, North Bridge, or they able to connect processor with another processor. So this technology by Intel, it is called QPI. In AMD, it is similar, but the name is different. But I think the most important is you to know how it works. So in this example, QPI consists of 84 physical wires, but the wires are grouped. So 2 wires create something which is called lane. And we have 20 lanes, so differential serial interfaces, which are used to send data, and 20 lanes for receiving data. So in this case, you can see that we have set of serial interface, and this is called a parallel set of serial interfaces. So we don't have a parallel interface, but we have serial interfaces which are able to send data independently, and this data can be then merged, but there are no problems with bit races, with crosstalks, because we have differential transfer, so there are no problems with crosstalks. And what's more, we can connect these lanes to different devices. So some of them we can connect to North Bridge, some of them we can connect to different processor. So our processor using QPI, so here you can see this scheme. So particular processor using QPI can create direct links with different, let's say, not devices, because QPI is limited to communicate between processors and communicate with North Bridge. But you can see that it is able to exchange data directly. The QPI is one of the fastest interfaces on your computers, but you can see that the throughput in one direction is similar to FSB. Yeah? So it's not so huge improvements. The throughput in 2 directions, so if we use all transmitting and receiving lanes, is 2 times higher than FSB. But the difference is that we can send data simultaneously, so we don't need to wait for when transfer from particular subsystem will be finished, like it may happen in case of half duplex bus architecture. What's more, if something will happen with lanes, so a single lane will be broken, our system is able to operate. Only group of 5 lanes is turned off. Okay, So the final slide is about memory controller. So look, the memory can be handled directly by processor controller. So it is the controller is embedded into processor. The processors, server processors, have up to 3 channels, so they can read and write data from using 3 channels at the same time. In personal computers, we have also we have usually a dual channel technology, so the processor is able to operate with 2 channels. So if you have 2 memory disks, the processor can communicate with every disk at the same time. So look, here you have a scheme for DDR3, so it's quite obsolete, but okay, it's valid also for DDR4 and even higher. But look, here you can see the bus. So the memory controller is the only interface in current computers which is parallel. So here we have many lines, so more than about 100 lines. They are physically, every line has the same length. So we are able to avoid a bit race effect. And it operates on frequency higher than 1 gigahertz. So using this technology, we are able to achieve a very high throughput. So here you can see that it's about, for DDR3, yeah, it's about 17 gigabytes per second. For DDR4 or 6, it's higher. And here you have different slots, and every slot, so slot 1, slot 1, slot 1, they belongs to single channel. So they all memory pieces which are placed in this slot are handled using a single channel. So if you have 2 memory pieces, it's better to place them in slot 1 and slot 0. So in this case, we can achieve the 2 times higher throughput because the controller is able to read and write data from this channels at the same time. Okay, so I think that's all for today. We will continue tomorrow. So thank you for your attention and goodbye.
Excuse me.